our spatial awareness is very, on hearing terms, is very related to our communication and our social animal nature. And spatial hearing is really critical to being able to even explore this thing in any way. Anyone who's got, for example, a hearing impairment or one-ear hearing impairment even has a really tough time in spatial listening. And what Paul was saying about the architectural perspective, oral architecture, I don't know if you know this book, it's by Barry Blesser and Linda Ruth Salter. Does anyone know this book? It's a Spaces Speak, Are You Listening? Now Barry is old school engineering MIT, and his wife is actually a sociologist. And so they sat around the dinner table wondering what they could do together, and they came up with this book. But Barry's a really sort of, I met him a few times and know a lot of his friends because they work in more mainstream perspective of what I do. But their book, Spaces Speak, Are You Listening, really demonstrates that it's the eventscape, the things that are happening out there that we use our ears to connect to the environment. And when people have problems with their hearing, they have problems with that. They feel disconnected from their environment when they don't have the soundscape. For example, you probably all know about anechoic rooms where there are no echoes and you've got those foam wedges. Animals that naturally nest in corners get very confused. They go and nest in the middle because they have no concept of a safe place that's got this sort of reverberation, so I stick my ear closer to here, that tells them, even in the dark, that they are safe and connected to their environment. So the whole soundscape, and what Barry calls the eventscape, is actually part of our being. And what I'm going to do today is really talk about, I think they're going to be the basics. I always think of them as the basics of spatial hearing and how the brain does it. But of course, for people who haven't experienced a lot of biology, any biologists in the room? Okay, one. So I will not be insulting your intelligence, I hope, but I will also try and bring you through how we generate this sense of auditory space, both with respect to other people and our sense in it, which often means in an environment such as a rectangular room. So I'll give you a brief overview of how we hear, which may seem pretty dull, but actually hearing the auditory scene, we don't think about hearing as much as we think about our sense of vision. So it's just useful to understand how the mechanics of hearing actually works. I'll then tell you that 2 ears is good. It doesn't just keep your glasses on. It's good for stereo vision. If you've got glasses, it's good for stereo hearing. And it's actually critical to our ability to create a sense of space. I'll talk a little bit about hearing at the cocktail party, because our ability to do cocktail party listening is phenomenal. We have abilities that if Siri could do it, then Google or whoever makes Siri, I don't know, Apple, have that Apple, I guess. I never use Siri because it's hopeless. It doesn't work in noise. It couldn't separate out one speaker from another, and it needs this huge buffer of time relative to what you use to do the same sort of thing. So the technology that we have for spatial hearing is rubbish compared with our abilities as human listeners and many other animals. And I'll talk at the very end about restoring spatial hearing, because when you lose your sense of spatial hearing, and that's generally associated with losing a sense of hearing, you can get hearing back, or communication abilities in particular back with respect to devices like hearing aids and cochlear implants. But restoring spatial hearing and connecting people to their environment is one of the things that goes missing when people have hearing therapies. They don't get that sense back, and it's very troubling. So how do we restore spatial hearing? So let's look at how we generate that sort of, the very basic nuts and bolts of hearing. I just want to show you this video. You've probably seen it before if you watch nerdular television.
It's prey moving about below. It must take great care not to scare them away.
Everyone seen this? So it's 6 feet above its prey. Can't see it. So our sense of hearing and our spatial hearing isn't about architecture, it's about survival and reproduction. Feeding, survival, reproduction. That's why we generated this. And of course, ears evolved from the lateral line organs in fish, which was sensing other fish, and that's why you have your balance organs in your ears as well. So it's about survival. Where are you? What's that? That's reverb, right? Heavy reverb. And what's creeping up on you is that. So generally, when we're in those sort of sounds, you already know the feeling of that. I might stop that. You already know the feeling of that because the spaciness of that, the reverb, the long reverberation time there provides a sense of being in a large space. And often in modern days, that's about being crept up on the space by that. No one can hear you screaming in a vacuum, but in the spaceship itself, that reverberant sense is actually something that can say there's something alarming, or we're in this open, vast area and not so and connected, yes, but maybe not as well connected as we should be. So we have survival for spatial hearing. We have that sense of being somewhere with reverberation, and all of these things play into our sort of acoustic or auditory scene. The other thing that we probably it's old dog's new tricks, or grandmother's suck eggs, that's the one. Architects probably think about auditory space with respect to rooms that they are actually working in. They can go from the very anechoic room, but to handling something in the wet. These two extreme environments here for reverberation are very clear to you if you were blindfolded and led into one of them, and you just had to speak or something like that. So you don't need information about that from any visual cue. You know, because you've built up a statistical pattern of what sounds are in which environments to reconstruct these spaces in your head, if you like, without any other input. You can just do it from the auditory input. And those of you who've been in an anechoic room, we have one at the Ear Institute, it's not very, it's quite disturbing eventually. Ours has a trampoline floor and can be pitch black. So that lack of sensory input, particularly as your tinnitus starts to rise, as you get no feedback from walls, etc., it is a disturbing feature. But what's important about what we do in the real world is that's not the real world. A lot of the real world is that. And we manage to perform well in the wet listening conditions, even though that is a very unattractive place for our brain signal processing to work, because it's a very reverberant and noisy environment where a direct source may be swamped by all the reverberation, but we do it very well. So how do we make a sense of where things are in the auditory world? If you think of the other senses, the special senses, if you think of touch, there's the homunculus, the sort of body map of where things are. It's mapped onto the sensory surface. And if you look at the cortex, the sensory, and the motor cortex in the brain, then you can see there's a map of where things are, about where things are. So it's mapped across the brain surface. If you think of sight, the back of the eye, the retina, has a map of where things are in space. So it's right at the very sensory end organ. And it's mapped across into the occipital lobe according to space in the visual cortex. So space out there, onto space receptors, up to the brain and mapped as space. That's not how the auditory system works. And the notion of creating a sense of space means that the brain really has to do quite a lot of work to retrieve space from cues that are not spatial. And yet, sounds have an out there-ness. Close your eyes for a minute. You hear that up there, the projector, there might be other rustling things. You have a sense of out there-ness of sound space. Even when it's quiet, you know a sound space. So sounds sound like they're coming from somewhere, but we don't have in our ears maps of where things are. What we have in our hearing is essentially all of the mechanics, but none of the deconstruction and reconstruction. So,
good news, everyone!
Professor Farnsworth, some music and some traffic noise. They don't come color-coded and they don't come sequentially. They come as
Good news, everyone!
a single unidimensional wave that comes and arrives at your ear as a single waveform. And depending on your attention, what's louder, what you're trying to do, trying to cross the road or listen to someone, you can attend to all of these things. But the only thing that's happening is that air molecules, or the pressure of air molecules either side of your eardrum is changing in a single unidimensional way. That none of those things exist as an object. They're just a change in your eardrum movement.
Good news, everyone.
So all of that's going into there, into your eardrum. And if you think about it, it's a bit of hand waving exercise. Your eardrum's moving backwards and forwards like that on each side. And from that, you have to extract all of those things as individual objects in different places. Now, if you look at the ear, there it is there, that's the ear canal, there's the tympanic membrane or the eardrum, the little bones, the ossicles of the bones. There's the cochlea, and there's the balance organs. The cochlea is the hearing organ, and if you roll it out, there's a membrane running down the middle, it's fluid filled, there's a membrane running down the middle that's actually resonant. It resonates at particular frequencies along its length. So put that in there, the cochlea divides up all of those frequencies that are in that complex sound into different parts by virtue of the fact that at the basal end, this end, it at the basal end, this end, it vibrates at high frequencies, and at the apical end, it vibrates at low frequencies or low pure tone pitches. And it takes, if you know the Fourier transform, it basically takes the signal and converts it into all its tonal frequencies, and then spreads it out across activation patterns across here. And if you look at that membrane, sitting along that membrane are the little sensory cells, the little hair cells, which if they go bald, you go deaf. These are the little sensory cells. I won't talk about these ones, which are called outer hair cells, but the inner hair cells, these are the inner hair cells, and they've got little hairs projecting up into them. And if you look at one of those, this is it here. This is a hair cell. It's got all these structures called the stereocilia, or hairs at it. And every time this membrane bounces up and down, as you saw in the last time, what happens is your eardrum does that, the ossicles push into the cochlea, the basal membrane does that, and the little hair cells sitting on top jump up and down, and their hairs are pushed backwards and forwards like that. And every time they're pushed in one direction, they open a little channel, and some ions flow in, and then you generate a nerve impulse. And that's the first way that sound information turns from mechanical energy about the sound coming from the speaker to your brain. And that's your brain sitting there. That little cell isn't your brain. Those cells, those nerve fibers, is the first point you get those action potentials or electrical pulses that go to your brain. And that's how you turn the sound in one ear into electrical activity. But that activity is not anything to do with where the sound source is or what the room is about. It's called tonotopic because it's organized according to frequency, from high frequencies in the cochlea at the base to low frequencies at the apex of the cochlea. That's just another view of it. And if you mapped it up to the cortex, auditory cortex sitting over here, then you can see it's each of the pieces of tissue here will have neurons in it, and each of those neurons will be more sensitive to one of these frequencies, sound frequencies. And in fact, if you take one end of the cortex and the other end of the cortex, it's mapping pure tone frequency from one end to the other. So where's space? That's what you see in the visual system. The eye maps to space, touch maps to space, but where's auditory space? Because that's auditory pitch. That's how high or low pitch something is. But space has to be created from stuff that isn't about space. And the fact that everything feels like it's out there in space is a construction from our brain. It's why we need an auditory brain, because the big grey wobbly bit at the top isn't the only bit of brain you have. If you think of all the things you have to do in this cocktail party, you need factors such as the vocal tract length, which tells you what your voice pitch is going to be, maybe male, maybe female. It separates out different talkers in a complex environment. It's also going to tell you about how many people are in the room, because you'll be able to hear complex perspectives, and location is going to differ. So that's how you have to parse the acoustic scene. But you do it not just with this bit of the brain, but all of the pathways that come up here. And in fact, it's much more complex than even this. This is the auditory cortex, the wobbly bit at the top of your auditory system. All of this is your auditory brain before you get to the wobbly bit at the top. That's the hardware. That's the stuff that actually does signal processing to compare, in this case, sounds coming to the two ears, which I'll talk about in a minute. This is the software. If you get this right, then you create the sense of space. You learn French. You can do all the complicated tasks. you can speak language and communicate effectively. But the hardware in the auditory system is stretched out. There's lots of stages of hardware, and part of that hardware in these structures here is about computing auditory space and the spatial cues. So I'm going to tell you about those spatial cues, and the majority of them, or a lot of that space, is about having two ears. So two ears is better than one. It's not just one ear plus the other ear. You can do things with two ears that are just not possible in any other configuration. And it's not just adding the information, it's sort of multiplying that information up. So two ears is essential for good spatial hearing. This is Lord Rayleigh. So Rayleigh was the polymath of polymaths. This is his house in Turning Place in Essex. Lord Rayleigh, anyone heard of him? Baron Strutt. He discovered why the sky is blue, obviously not in England. Rayleigh scattering, so it's about optics. He did a lot of work on optics. He was a sick and feeble child and didn't go to university or school, but he worked in his lab at Turning Place. And he's the person we credit with discovering how we use two ears to be able to tell where sources are located. The guy above him is Sylvanus Thompson. Now, unfortunately, Lord Rayleigh back in the day was Lord Rayleigh, and the only intelligent people clearly came from the upper classes, and so they had all the time to do science. Sylvanus Thompson, prior to Lord Rayleigh, who was a grotty engineer from Bristol, actually discovered this. But what they found were the cues that tell us how we actually tell left from right. Something as simple as left from right. Now, back in the day, people knew one of the cues for telling left from right would be the fact that you have two ears and a sound over here is louder at this ear than it is at this ear. So they could say, well, the difference in intensity or loudness between the two ears tells me the sound's over on my left or over on my right. But they weren't stupid. They also knew that as the sound pitch goes down, the wavelength increases and the wave just moves around your head. So below about 2 kilohertz or 1.5 kilohertz, there's no head shadow, as they call it. There's no shadowing of the head to tell you that something's on the left or the right. So there's no intensity difference because the wavelength's so long. So they said, well, what other cue is there? And then, there's the time difference between the two ears. A sound over here arrives earlier, and then it arrives here, and there's a time difference. And that can tell us that the sound is over somewhere in space. But they also thought, well, hang on a minute. Over there, the speed of sound is 343 meters a second. The sound's over there. Maximally, that can be 670 millionths of a second for the sound wave to reach my other ear. And they thought, well, that's impossible. And in fact, we know you can detect 1 degree off the midline. You can detect a sound move by a degree, which is about 20 microseconds, 20 millionths of a second, which is faster than any action potential, any neural impulse in the brain. So this is impossible. What is it? So Rayleigh and Sylvanus Thompson before him used something called binaural beats to demonstrate that we're sensitive to the time difference between the two ears, and that's the main cue we use to tell left from right in auditory space. Now, who's heard of binaural beats? Binaural beats are a bit weird. You may have seen them with respect to some hippie, trippy looking things on the interweb. This is great. Did you know there is a new type of music called binaural beats that can make you high and trigger special dreams? This is the world's first digital drug, and I'll come back to that. And this is my absolute favourite, binaural beats for the shamanic journey. So Rayleigh first used binaural beats. Oh yeah, why is it a drug? Because some freaky people on the interweb think that putting binaural beats on, and I'll tell you what they are in a minute, actually makes people high and tunes into the rhythms in their brain. Now, it all sounds very cool, and people are suggesting that we should ban binaural beats, but they're a really prosaic, very simple stimulus. They're essentially what Rayleigh and before him Sylvanus Thompson used to demonstrate that we can use the very small timing differences between the ears to create space. So in his study anyway, it was, for this experiment you'll need 1 stately home, 1 butler, 2 gazebos, 1 wife, who was the subject, 2 pieces of rubber tubing, and 2 slightly mistuned tuning forks. And the idea was to strike the tuning forks in separate locations and pipe the sound from the 2 ears to the 2 ears, 1 tuning fork to 1 ear and 1 to the other. Now the slight mistuning is only at 1 or 2 hertz difference between the two. And if you were to listen to one at one ear and then the other, you wouldn't be able to tell the difference. The difference in frequency of those tones is too little for you to be able to discriminate the 500 hertz from 499 hertz, for example. But your brain sees those as different if you put them to the two ears. It perceives them very strongly as very different. It doesn't hear two sounds, but what it hears is essentially a sound. If the sound is, say, 500 hertz in my right ear and 499 hertz in my left ear, you present that over headphones and you hear a tone in your head which starts to move inside your head, go from one side to the other. It's sort of and the reason for that is at time zero they start in phase, but the 1 hertz difference means about half a second they're 180 degrees out of phase with each other. It's like having a sound that's off to the side. And over another second, they come back into phase. So what you get is this perception of this rotating tone going around inside your head. And Rayleigh, using his wife, the butler, 2 gazebos, 2 pieces, the standard laboratory technique of the 1800s, was able to demonstrate that we were sensitive to these fine timing differences, a fine time structure, the time difference between the two ears, and demonstrated that we were sensitive to that. And that is our main cue below 1500 hertz for telling where sounds are located in space. Above 1500 hertz, it's the head shadow. So your head is shadowing sound, and you have these 2 cues. And they're not actually, and there's a crossover point where they're not very good. So around 1,500 to 3,000 hertz, your spatial hearing isn't quite as good. There's a bump in performance. And strangely, that's our area where our speech frequencies are very important. So why our perception hasn't changed that, or maybe our head size changed so much very rapidly, and to accommodate our speech frequencies, we don't know. So we have intraoral level differences for high frequencies, intraoral time differences for low frequencies, and there are different brain structures, which I won't go into too much detail, but I'll show you a cartoon. The pathway that detects level differences is this one here, which have excitatory activity from this ear and inhibitory from that. And the ITD pathway is in the brainstem. There's the cochlea on both sides. It compares the signal of the 2 ears and actually extracts the spatial information. So what I want to do is, I'll show you the video of how this is done, but I want to give you a bit of, give some exercise, get some oxygen flowing. So I'm going to show you how, or tell you how you can tell where sound is located in space. So everyone do that. 2 hands. So this is the diaphragm of a speaker. But let's just say the diaphragm of a speaker with 1 hand, right? Because that's just one source, right? But you've got 2 eardrums, right? Well, let's put the speaker there, right? Don't hit the person in front of you. There's a diaphragm moving, and therefore there's a pressure wave. And back to here. And here's your eardrums, right? Moving in and out, moving in and out. And that sends all this chain of mechanical activity to your basilar membrane, that membrane that runs along the cochlea. And there it is. This is like the birdie song for those of you old enough. And that's your basilar membrane moving up and down. And sitting on top of those little hair cells. And the hair cells are doing that. Well, the stereocilia are doing that. And every time they go in that direction, it opens up a little ion channel and it causes a neural impulse. Okay, so that's the stereocilia. Come on, hands up. Don't worship me. And this, every time you go up, tick. Say tick. 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 That's a little neural impulse from the 2 ears. Right? Tick. 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 Right. Where's the sound source that's doing that? Where was it located? Tick. Tick. That's both ears going in sync. Where is it located? The source.
In front.
Or?
In the back.
In the back. Good, because front-back confusions. You can't tell front from back based on time differences. Great. Blindfold someone, play them a tone from there, or go that way. It's because there's no, it's all ambiguous. But there you go. Tick, tick. Now, move your head. Hands up. Hands up. Now move the source, or move your head left or right. What happens to the ticks? Tick, 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 tick. They go out of sync because they're not reaching your ears at the same time. The source is now somewhere off to the side relative to your head. If you had a brain mechanism that could compare the ticks and cancel them out, you'd have a map of space. That's what you have. So it's called a coincidence detection mechanism. Lloyd Jeffress, before there was any brain biology of this known, came up with this cool model. It'll go quickly and then go slowly again. I'll orient you. These are the two cochlea, the ears. This is the first neural stage of processing. And these things are called coincidence detectors. They're neurons that essentially, as an array, are an array of a neural map of space. These wires are the axons, the things that connect to neurons to each other. And this elegant little model will show you how your brain turns information about the relative timing of sounds into horizontal space. Let's see if we can run it. It'll go quickly and then it'll slow down, so I'll hopefully talk you through the first one. So this is a single pressure wave of a sound wave. They're neural impulses, and that is some sort of brain activity. Now watch it in slow motion. The sound's in front of you. It hits both ears simultaneously. It generates a nerve impulse. It hits these two structures at the same time. It goes down these wires. These are called delay lines in the parlance. And it hits these numbered balls, which are neurons, but only at number 2 do they coincide. And when they coincide, the neuron responds. Now, here's a sound off to the side. It's going to hit this ear before this ear. Now this guy's got to catch up. How's he going to do it? Well, he doesn't have to do it because somewhere in there's a delay line that offsets the lag he had, and this guy responds. So just across this array, by these wires coming in, you've created, from 2 ears that had no knowledge of space, a map of space, of horizontal space. So you generate this space at a very early stage. These neurons are telling you about what your eardrum is doing. And that's very unusual because you're 3 stages above the ear, and yet they're keeping information about your eardrum movement, which is a very long distance away in neural terms. So that's the coincidence detector model. What I've told you already, the horizontal plane, head shadow, and interaural time difference. These are the 2 cues, and we rely on interaural time difference for many other things, including cochlear particles. But the world is more than horizontal. It's also elevational. And this is Alphonse Bertillon. Back in the day, before fingerprints, Alphonse Bertillon was trying to separate out the criminal underclasses, and here you see 2 members of the criminal underclass. Completely indistinguishable from each other, but for the fact that their ear shapes are different. And Alphonse Bertillon came up with the idea of unique ear prints before fingerprints, that actually you could find out the criminals and sort them out based upon their ears. It was all at the time of Galton and all that sort of eugenics stuff. And obviously the only thing that happened, there were an awful lot of Parisian safecrackers arrested in the first few months. But once they had fingerprints, of course, this fell out of fashion. But he decided you could actually have a unique representation of people by the shape of their external ear. And it's true. There is a unique representation by your external ear. And your external ear is what gives you elevation. It tells you up and down. It also disambiguates front and back. If you didn't have these, everything, even in a complex sound, would sound like it could be on the front or back. And we know that because if you put a microphone at your ear, the entrance to your ear, and one on your eardrum, you see a very different sound. So if you take a single sound source and present it from anywhere in the world, the sound that it reaches your outside your ear will be the same unless there's anything interfering with it. But if you just think of a direct path from anywhere to your ear, from a single source that you move around, the sound should be the same, but just as it reaches your ear. But when it reaches your eardrum, it's radically transformed. And it's transformed by all of this shape of your pinup and your concha. It basically gets boosted in sound energy and reduced in sound energy. This is a map of what your ear does, and it's a unique map. It differs for different people. Some people have better virtual hearing. So you've heard of these stereo sounds where you have the virtual sound where you can actually hear externalized sounds, and that's because people have recorded with microphones on the eardrum, and they record the full effect of the pinup on the sound. So all these hot spots here, this is elevation, above or beneath the horizon. This is the sound frequency. And if you put in a sound like shh, where all the frequencies have the same energy in them, your ear reduces the energy in some and boosts the energy in the others. or the other way around, that's an increase in energy and a reduction in energy. It's a unique pattern for a unique place and position. So as you go across the horizon, you can see that each of the sound frequencies has a map, has an increase or a decrease in its energy. And as you go up or down above the horizontal, this pattern is very different. And you learn this. Your brain learns to associate a unique pattern, a map like that, with an object in a spatial position. What's cool about this is you can put on a different pair of ears. So this study by Hoffman et al. In '98 put on a different pair. They basically blocked up not the ear canal, but this bit here, with some rubber, some putty that you would put in for ear molds. And what you see, just by doing this, is it changes that, what we call Pinup Transfer function. It changes the energy that the ear adds or subtracts from the sound when it hits your eardrum. So this pattern looks very different there to there. Now I often think they used vulcanized rubber, but I have wondered what it would be like to listen through Star Trek ears. There's got to be a nature paper in the spatial listening capacity of Star Trek characters, because that's really. I'm sure Spock, when he put them on, was thumping his head on the tricorder or whatever he used. But anyway, does this have any effect on you? Does it impinge or impact on your spatial listening? Well, yes, because what Hoffman and colleagues did was they took a 4x4 array of speakers and they hid it behind a curtain, and they basically got people with their old ears and their new ears to do a task. They stood them in the front and they said, okay, we're going to present a sound, you can't see the speaker, and just present, click with a laser pointer where you hear this sound coming from. And we'll map your laser pointer points to reality, where the sound actually was coming from. And here are the data. And concentrate on this one first, ignore these. This is one subject, MZ. I wonder what the surname was. This is the responses. So this grid here is where each of these points is where the speaker was. This thicker bar with the data points is the average point at which people pointed to, and they're pretty good. They don't get it canonically, but they get it reasonably well. It's still a square that you can recognize with points that are at the intersections where the speakers are. But when you give them new ears, everything goes to the horizontal. They lose their sense of height, of space. They're just now hear everything on the horizon. But over a month, they get a new sense of new ears. They learn their new ears. They learn the acoustic environment through their new ears and remap a sense of height, of space in that dimension. So you can mess around with this. And the cool thing about it is, after a month, you've got your new ears imprinted somewhere in your brain. You take your new ears out, you've got your old ears, but you have them instantly back. So this is your old ears again, instantly. That's not like wearing prism glasses, which take a few days to readapt to the real upside-down, non-upside-down world. You've got your old ears. So somewhere in your brain is a map of where all of this stuff is taking place and integrated to give this spatial representation. Don't know what happened there. Yes, I do. Hearing at the cocktail party. It's all very well to have spatial cues for horizontal stuff, for elevational stuff, but really the issue we have is not assessing where things are. For us, it's about communication. When we think of spatial hearing for normal hearing human listeners, it's about their ability to communicate in complex environments, where there are other people talking, where there are rooms. And people who have lost their spatial hearing abilities, generally because they've lost their hearing abilities and had some sort of therapy, yes, they're okay and quiet. Yes, they can orient around space when it's not complex, but once it's complex, once there are other people in the room, everything goes to pot, because what they're really losing is their spatial ability in communication. Communication is a spatial thing. So if you think about the cocktail party problem, you've all heard it called the cocktail party problem. You know, how do we do this sort of task where there are lots of people talking, and yet we can hear out the conversation? And of course, things can change, our attention can change. We can hear the clink of a champagne glass, the click of a stiletto heel on a marble floor. Those sorts of things attract our auditory attention here, there, and everywhere. But we do this communication in very complex listening conditions very well, effortlessly almost, and yet the cues that we use to do that are the spatial cues and are very easily lost in people who have problems with their hearing. Now, back in the day, the term cocktail party, I am very pleased to say, was designed by Colin Cherry and Bowles. I mean, Cherry and Bowles at a cocktail party, I mean, that's got to be, I can't believe this is true. But this is true, this is Colin Cherry, who's a professor of engineering at Imperial College. And so back in the 50s and 60s, this was the first time people were thinking about this problem. And they were thinking about it because they were starting to think about how you would do it in an engineering system, building systems that would actually extract information from complex listening things rather than having the human brain. So it's Colin Cherry, Bowles, and Sayers again, cocktail parties. That's got to be, a joke. But really, what problem? We do that effortlessly in complex listening conditions. And a data slide showing you indicative data. This is how many words people get correct. High is good, low is bad, as a function of how loud the what they're trying to listen to, the target, is compared with the noise or the interferer. And you can see that even when especially if there's a single other talker, even when they're louder by 18 decibels than what they're trying to listen to, they still get it right more than 50% of the time. If it's steady noise, like shh noise, they're still doing better than chance, well above chance, at -3 decibels. In fact, they're doing 80% performance. You've got to get all the way down to 6 decibels quieter than the noise before you take a hit of just 50-50. That's an incredible ability, and it's our spatial hearing that does that. And the other thing we're really good at is reflections. Unfortunately, you're not in a cocktail party. You're here in a warm room listening to me banging on. And what's important is that most of the sound energy from my voice is not coming to you direct from my voice, it's coming from the walls. The direct to reverberant ratio, how much of my voice is coming to you as opposed to and at the back, it's even more reverberation. In fact, if there weren't reverberation in this room now, people in the back would have difficulty hearing. Because the reverberation off the back of the walls there is allowing you to pick up extra energy to hear my voice. But you could close your eyes, and some of you may have already, and you still know where I am. Because even though I'm speaking here, and you can see the red curve of the speech, the green, long, reverberant tail is the energy you're hearing. You don't see the red. You don't have the red information, but your brain picks it out. And your low frequency, the ITD-sensitive part of the brain, essentially picks out glimpses of information. Every time there's a little quiet spot in the sound, the next thing that happens has to be the direct source, not the reverberation, not the room. And our low frequency system grabs that information the minute it comes in and says, that's the spatial location. Everything else is noise. Everything else is the room. And our important aspect of our spatial hearing is that we divide foreground and background. And if we don't have good spatial hearing, we have difficulty in these reverberant listening conditions because we can't separate out what's the foreground, the object, from what is the room, what is the reflections, all of the energy that comes back off the walls and that actually tells us whether they're in the bathroom or in a library. And so it's very important, therefore, to keep it, what I call keep it binaural. You must have 2 ears, but you can't do 2 separate things with 2 ears and try to get binaural hearing. I'm going to do a little experiment with you again. Just have to wet my whistle. So I'm going to give you 3 noises. And you're going to tell me which of 2 and 3 is different to 1. Okay? Here's noise 1. Shh. Here's noise 2. Shh. Here's noise 3. Shh. Which is noise 2? Shh. Or noise 3? Shh. Is different from noise 1. Shh. I'll play them again. Here's noise 1. Shh. Here's noise 2. Shh. Here's noise 3. Shh.
3 was different.
3.
Well, who thinks it's 3? Who thinks it's 2? Who thinks it was a completely mad experiment? Yeah, because if you think about it, all of those sounds had all of the same characteristics in terms of frequency content, my larynx, everything like that. They're roughly the same. In fact, you would have a hard time saying which was different. But actually, they're all independently generated pieces of noise. And if you listen to 1, 2, and 3 in this ear, you wouldn't know if any one of them was different, or you'd have a very hard time knowing they were different. You might just be randomly saying 1 or 2 or 3. But if you put 1 in one ear and 2 or 3 in the other ear, you instantly know that they're different, because your brain is smarter than you are. It essentially says, well, these are completely different sounds. They may sound roughly the same, but actually on their millisecond, microsecond by microsecond, they're completely different. And so if you play 1 to one ear and 1 to the other ear, and it's the same sound, so 1 and 1, what you hear is like stereo headphones. You hear a sound inside your head that's there. Shh. And if you change the time so it's slightly arriving earlier at one ear and the other, then it moves around like that inside your head. You don't hear 2 sounds, you hear one fused sound image that moves around your head as you move one later or earlier in time electronically. But if one of them is a different token of noise, a different piece of noise, that's noise 1 and that's noise 2. Your brain knows, hang on, they didn't come from the same source. One of those must be a different source, or this is reverberation. And what you hear when you hear sh in one ear, sh in the other ear, you hear the background. You hear the space in which you're listening. So if you listen to those over headphones, you hear a fuzzy ball of a sound. You don't hear a compact image like you do with your headphones for music or anything. You hear this sort of amorphous blob. And your binaural brain is essentially comparing all of the small differences between the 2 ears of a sound. If I'm standing here with my ear very close to this wall, all the reverberation is changing the sound I hear, so that I'll already be separating out sounds I hear from this direction, from that direction, based upon the difference of the sound at this ear and this ear, by the fact it's reflecting and bouncing around here. I'll know I'm close to this side, and I'll know I'm in this type of room, just from those differences. And the smaller the differences, the more it's going to be the object in the room. The bigger the differences, the more it's the room. And that's what reverb does. That's when you have lots of people in the room, all their voices interfere, and you hear this background amorphous hum, because all their sound is arriving, interfering, and it's different at the 2 ears, and it becomes the background. So your binaural brain separates things into object and background. And that's separation is critical to our sense of well-being. We don't have that sense of spaciness or space, then we don't feel connected. We'll move through that. So just a couple of slides to tell you about paradoxical things that tell us why this might be important. Statistics. We all hate stats, but what we mean here is, how does our perception take account of the unrolling environment that we're listening to? And how do we use it to tell us what's foreground and background in space? This is a paper by Josh McDermott and his colleagues. Summary statistics on auditory perception. And it's a really cool little experiment. Human perception. And it's about textures. If you think of textures like a fire, or water running, or leaves crackling, and you can ask people, okay, can you tell the difference between these 2 textures? So the texture sound of water running versus from fire. And you can give them 3 examples. That is going to be 1, say it's fire, and that's a different one, that's water, and that's the same as 1 again. Something like that. And so you ask them simply, is 2 or 3 different to 1, just like I asked you before. Well, what happens is, if it's very short, they have no idea, they don't get it right. But over time, if you increase the length of that piece of texture, as it gets longer, 2.5 seconds of sound, they get better and better, and they're almost perfect at saying, well, one of these was the same as this one, 2 or 3 was the same as this. You're always asking them to say, is 2 or 3 the same as 1? 2 or 3 the same as 1. And they get it right 100% of the time, at 2.5 seconds. Contrast that with exemplar discrimination. What that means is, I've got a piece of fire noise, and I'm going to give you another piece of fire noise, and are they the same or different? Now, if you listen to it very short term, you can actually tell the difference. Really, the spectral changes, they're different, because one was record the fire, and the next record the fire. They're different recordings. And your brain says, okay, I'll have that as a very short snippet of it. I can tell the difference between these 2 recordings. But look what happens the longer you listen to the fire. Performance goes down, because you're not interested in that background sound anymore. After a couple of seconds, I don't want to tell the differences. I want the long-term statistics to say, that's the background, it's not important, I'm just chucking it there, and I'll leave that as my background. So I don't want to distinguish that snippet from that snippet. I want to say, that's it, I know there's a background of a far sound. Doesn't matter if it's different or anything, and you start to lose the ability to tell the difference between the two. So discriminating different sounds, you get better as the sound gets longer. Discriminating a different version of the same sound, you get worse. Because it's the background. You want to adapt the background out so you can listen to what's going on. And use the background as something you're listening against, not what you're trying to discriminate. And our brain's really good at that. You can move between these two environments, from the cocktail party to the balcony, and the whole acoustics changes, and it takes about a minute to learn that scene. Acoustic, we have evidence, which I won't show you, that says it takes a minute to learn what's going on in a scene. And as you learn, you get better at processing it. You then switch to a different scene, maybe a quieter scene, and it takes about a minute to learn that as well. If you keep switching backwards and forwards, so have a drink, go out for a fag, have a drink, go out for a fag, that sort of thing, as you do at a party. Some people do at a party. Not that I'll mention anyone. It gets faster. You learn the scene faster and faster if you've experienced it before. And so things that you do in the scene, discriminating voices, knowing what the room is like, you do faster and faster every time you're repeatedly exposed to it. That's a brain trick for learning the scene and then having it imprinted in your brain. Very briefly, I'm going to talk about restoring spatial hearing. It's a huge topic and it's of huge interest because we're all losing our hearing, we're not getting any younger, there is no noise at play regulations, we're all deafening ourselves, and when you died, when you were deaf at 50, it didn't matter 100 years ago because you were dead 10 years later. Now, you're going to be deaf for half of your life. Think about that. And there's no cure, and our healthy lifestyles are not helping it because there's nothing we can do about it, except we're deafening ourselves more and more at play in social environments. And you know, the boom of the baby boomer generation is nothing, not the sound of amplified music. We have this huge tidal wave of hearing loss in this, and it disconnects us from our environment. There are many more successful deaf people in terms of the way we consider success in professions, etc., than there are blind people. Sorry, the other way around. There are very many more blind people who are successful than deaf people, because what you lose when you lose your hearing is you lose your ability to communicate. You don't just lose your hearing, you lose your ability to communicate with someone's spoken voice. So people who have lost their sight have much more adaptability to that than people who lose their hearing, because they're often cut off from the rest of the community, and they're cut off from what's happening behind them, over there, their connection to the environment. So restoring spatial hearing. This is me back in the day. If you lose something, can you get it back? For those of you who know the vernacular, that's the fine structure and that's the envelope structure for the acousticians in the room. But is it possible to restore what you've actually lost? And I don't mean hair, I mean hair cells. But can you restore spatial hearing? Now, there's nothing new under the sun. People have been doing this sort of thing all the time. This is pre-radar. So basically, you want to find out where the boat is so you can sink it. So you put on a huge elephant-sized head and make your interaural time differences this wide. And you've got this huge arc of space rather than your sort of narrow-headed arc like that. And the idea was to see or hear ships in the fog and then blow them up, I guess. So these are pre-radar devices using hearing to give you this wide spatial extent. But people have been playing with acoustics and with devices for a long time. We have hearing aids when people go deaf, but hearing aids are really bad for you. And first they end up in the drawer, because 80% of them end up in the drawer because they don't work. People go in and say, I'm having trouble with my hearing. They give you a test, which is tones are quiet, but people aren't having problems hearing tones. They're having problems at cocktail parties, at restaurants, listening to television, talking to their friends, communicating, working. So you test them on quiet, on tones, put a hearing aid, and off they go, and they chuck in the drawer. Because they're not listening in complex environments when they test them. And hearing aids don't help. They make the signal louder, but they don't distinguish it. And in many cases, with this closed ear fit, if you all stick your fingers in your ears now, and say your name, sorry, take them out. Stick your fingers in your ear and say your name. David. So which name did you hear? Which name did you hear? Your own, right? No one else's. because you've removed any capacity to provide that. Hopefully you heard someone talking to you. The beam of light is out. So essentially, by closing up our ears like that, it's not, we can amplify the sound in there, but it doesn't provide us with the spaciness that we lose that spaciness of our pinup that provides reverb and up-down elevation. And cochlear implants are the same. Electrical hearing. We can provide electrical hearing with this sort of hearing aid device that turns things into a train of electrical pulses, feeds them down a wire into your cochlea, and stimulates the nerves directly. But we don't have spatial hearing with these. Kids are now getting 2 implants, one for each ear. They can tell left from right now. People say, what's the evidence that this is better? Well, the evidence is in 20 years' time, how many people turned up in casualty having been hit by a car? You know, doing that when it's actually that way, basic. I mean, if we had a retinal implant, no one would say you should get 1, everyone would say you get 2. Space and the ability to tell left and right is critical to these kids as they grow up and develop, and it's critical for cocktail party listening. And we test this sort of thing with kids at the Ear Institute. Can they actually just do something as simple as tell left and right? And what you see here, in normal hearing, for 4 or 5-year-old kids, there's a big range, but most kids are doing really well at 90 to 100% performance, just telling left and right. How do you get kids to do these tasks? Kids with a unilateral implant are nearly a chance. They have no chance of just saying something's there versus there. I mean, that's a fundamental percept, and it's fundamental to our sense of well-being. It's fundamental to his social embarrassment. How do you actually cope with that sort of thing? Kids with 2 implants do much better, and they do better increasingly as they get older. So, the one place they really struggle in, of course, is that environment. Anyone who's got impaired hearing, even with a device, cannot separate out that from that. All they hear is reverb, because their binaural brain, the parts of the brain that does that rapid detection, just hears the green smear. So it's not that they can't hear where things are, they can't not hear where things are. Sound coming off the wall there, to you, is a source, and you hear that source. So you just hear this multitude of sounds coming at you. You don't have the perceptive figure background, with the reverb being the background in the room. You have this sense that everything's happening everywhere at once. And that's the issue for people with hearing impairment. Can we restore spatial hearing, which is the one thing they're missing, and they really need that perspective. And I'll finish with, before I show you, this is the critical thing for us. These sort of spaces, and I'm not going to tell architects how to design space, but acoustic spaces are really tough to get right, because people are very different about what they want in an acoustic space. Where they sit, where they move their head, how many people are in the room, all changes. And if you think about what's happening in here, it's almost certainly a lot of loud music playing. And people's oral sense of a space and their ability to communicate and work as a social animal is very dependent on whether they can actually hear, and where they hear people coming from, and what the background is, and how reflective the surfaces are. And adding background noise to this listening situation is okay when there's 2 of you having an intimate dinner and you don't want the bar staff to hear it. But once you've added this in, you don't need that extra noise. You want to have connectedness, yes, and you want to have intimacy, but you don't need it when you have an environment where there are many other people in it. They create the background, and that becomes part of what you're listening against. So I hope that's a very brief tour through the auditory brain. How we connect it to our sense of connectedness is evident with respect to how well people hear and how well they do in the rest of their lives. People with hearing problems, especially who don't feel connected to the world, they have social and other problems. They can often be depressed. Education and life chances are very removed from what many of us just take for granted because of the hearing. But the connectedness to space through hearing is actually the thing that people have disconnected from with headphones and with other technologies, rather than letting the sort of repertoire of sound escapes actually connect us to that environment. It's not easy to do it when you're walking around with headphones the whole time. You are disconnected from your environment. And that's something we need to get back to, a natural way of understanding our acoustic space in the same way that we would not allow our visual space to be so impacted. Thank you very much.
Thank you very much, David. Are you able to answer a few questions?
Yes.
Have they got any questions for David?
Because we
suggestions on how architects might make more special acoustic experiences, because we often spend our whole time in a kind of generic place for lots of absorption, but sometimes a bit of reverberation, a bit of reflection sound is kind of quite nice and quite interesting, and quite like a special experience.
Yeah.
Anyway.
Yeah, so I like reverb, but it's very hard for communication. So the issue really relates. So the Ear Institute has an atrium, which is terrible acoustics when you consider we're bringing people in there often who have hearing problems and having cocktail parties with them, and it's very echoic. But I agree, you should be able to provide specific acoustic spaces for the need, and that can change. So there are panels now which can give you reverberation. There are sound systems that can soak things up as well as put them out. But so I think it's not so much about one size fits all for any room. We've got to find ways of making rooms much more adaptable acoustically. We put sliders between doors. We do everything, but we never think about the space, the auditory space. And a good example was my baby brother's wedding in 2002. My twin brother is a minister of the church. This is in Australia. I flew out there for the wedding, and my twin brother is doing the ceremony. And I'm sitting near the back, actually. And it's a modern church. It's got amped up. So the minute, right at the "do you take so and so," the speaker system went down. I'm sitting, not here to the front of the room. Couldn't hear a thing, because everything had been designed for amplification and nothing for natural acoustics. Nothing for taking the room into account when you do something. And it just disconnects you. Unless you have amplification now, we don't get away with anything. And I think that's a problem. We've got to make places much more, yes, acoustically, churches are built and designed for specific acoustic and blah, blah. We've got to make our own spaces at least adaptable, but also not just depending on having a mic.
It's a nice argument for bringing the human back into architecture.
Absolutely, yeah.
Talking of which, I was thinking in listening to your talk that I've read that the human body hasn't evolved much, in the last 200,000 years.
Yeah.
So we're still sort of ostensibly we've got the hearing systems of cavemen. Has the sort of the evolution of architecture, which was Lao was sitting in a perfectly sort of shoebox shape, have we adjusted architecturally? Has our hearing adjusted at all?
Well, brains are very good at picking up the learning new environments. But if you think of the ability to use time differences between the two ears as a good example of why our heads have grown a lot more than our brains have allowed performance for, the frequency at which things become ambiguous, so the phase difference for a sound reaching the two ears, we can do it over headphones up to 1500 hertz, but our heads are so big now that beyond 700 hertz it's ambiguous. So a sound leading with this ear could be a sound leading with that ear, with slight phase difference. So the phase reaching this ear less than 180 degrees, or that reaching at less than 100 degrees, means that we're stuck for ambiguity below 700 hertz. So we haven't evolved much, and our hearing isn't very preserved. So birds regenerate their hearing because they needed it to sing, to get a mate, to survive. We never needed to do anything with our hearing before we procreated and died. And that's pretty much the problem. So essentially you're born deaf, that maybe tackle you out, but the fact that you lose your hearing very early in life relative to our longevity, there's no factor that allows us to keep our hearing regenerating the way birds do, because they had evolutionary pressure to do it, and we didn't. So our hearing is sort of stuck in that space. But we can do lots of interesting things with it, but mostly what we do is damage it.
It's the most precious thing, and all we do is damage it.
Yeah. Have you got anyone with tinnitus? Self-induced? Yeah. Noisy car.
I have a couple of questions. First one was when you were discussing about the sound is in your head or outside your head. That's just depending on if you're listening to the same sound, then since you cannot detect differences like the beats, then automatically there's no space for the sound coming from the outside, and your brain who's inside your head.
So externalization is a product of reverberation plus the Pinup.
Okay.
And so externalizing things, you need your Pinup. But if you add reverb to sound, then you can get an externalization per second.
Okay.
But
Or you have binaural recordings.
Yeah, but binaural recordings. But if you've got two sounds that are very similar to ears, you get a punctate image, whether it's in real space or inside your head or stereo headphones. If they're very different, the two ears, you always get a more diffuse image. And that's the challenge, is how to... And that becomes foreground, background. That becomes what we see as the object versus everything else.
I still have another question that is not too much related to architecture, but how sound is perceived by our brain. I think you have heard of ASMR, and
Automatic speech.
no,
ASMR. No.
there's kind of I've read a few articles recently about there is a trend. You can go on YouTube
Yeah.
and you can find a lot of channels where basically someone is talking to a binaural mic
Yeah.
and making different noises that could be speaking or whispering or stuff like that. Now, since I'm an acoustician and I'm always bothered by sound, I've listened as much as I'm ashamed of having done that to this video. And in theory, certain people are able to feel in tickles in their head and effects, and actually I can feel that.
You can.
It's makes a physical
Yeah. So
impact on me, but it's just sound. It only happens with the headphones and binaural. If I've tried with someone doing it in real time, but it doesn't really work.
because you could be synesthetic. Synesthesia is much more common than people think. So people have auditory experiences when they see colors, or they have colors when they see a word. It's got each letter of color, and I believe strongly that that's a creative space to explore. I think people don't do it enough with sound, and spatial sound is another perspective to sound in general. People think, well, hearing this tone gives me a color. But we think about that as chroma, so you could have potentially put it in the same sphere. But synesthesia, where one percept or one sensory system is bled into or influenced by another, I think it's very much part of the creative aspect. It's no accident that the people I've spoken to who are synesthetes tend to be in the creative fields, because they've got more connection to creative aspects. Having it with spatial here, that's pretty cool, actually. I must put you in a brain scanner and see what's going on. Sure, it wasn't just the headphones.
Yeah, it was moving and vibrating. I think so. I'll check it out tonight.
That's experimental.
Okay, any more questions? Okay, David, thank you ever so much, and please come back again.
Thank you.
Thank you.